So what I'm going to talk about here is basically an interpretation of the upper limits on the reionization epoch from MWA. So this is what Kath alluded to in the previous talk. So just a brief one-slide introduction to the reionization epoch. Here you don't have to take in the details of the equation itself, but what we're looking at is measuring the 21 centimeter brightness temperature of neutral hydrogen in the IgM against the background C and B. And so you can see here that this signal is sensitive to a lot of interesting astrophysical information and your cosmology as well. So you can see here it's dependent on the neutral fraction, which is a proxy for your ionization morphology. So what kind of galaxies produce reionization, gas density, so your density, spin temperature, which is about the heating of the IgM as well. And that's going to be one of the main focuses of this talk as well. And then, as I said, cosmology. And down the bottom, this is a simulated 21 centimeter signal. So you can see here that it's rich with astrophysical information. You have the morphological structure of reionization, and you also have large temperature contrast as it goes through different epochs from the cosmic dark ages down to the epoch of reionization. As Kath spoke in the previous slide talk, MWA has new upper limits. And so these are the 2 sigma upper limits. So I won't dwell on this too much further. I'll go to a less populated compilation of upper limits on the 21 centimeter power spectrum. So in the previous slides, I showed sort of the 3D morphology of the reionization epoch, but we're wanting to be able to measure, or at least the first detection is going to be in terms of a statistical detection, which would be the 21 centimeter power spectrum. And here you see a compilation of the upper limits on the 21 centimeter power spectrum from all existing reionization experiments, including the LOFAR point and MWA point. So this is just the lowest amplitude point. I haven't put on all the points to make it a little bit simpler. And as Kath mentioned, down here is sort of a representative example of where our theoretical understanding on the reionization epoch is. So this would be a 21 centimeter power spectrum from the theoretical simulation about redshift 7. And here would be if I was to modify the morphology of reionization, what types of sources were causing reionization, I can push it up to about here in terms of its amplitude, which is still at least an order of magnitude and a half away from where the limits on the existing signal are. So if we return to the brightness temperature equation that I showed previously, cull a lot of the terms, left here with sort of the ionizing morphology, the gas density, and the temperature of the IgM. Now, these vanilla models of the reionization I was talking about before, we assume that the IgM undergoes some form of heating. So this may be from high mass X-ray binaries. X-rays escaping the galaxies go into the IgM, propagate far, cause secondary ionizations and heating of the IgM. Under these kind of scenarios, you expect a brightness temperature contrast of a few to tens of millikelvins. And the power spectrum is the brightness temperature contrast squared. So you can get signals of order tens to hundreds of millikelvin. So that's sort of where you sit in terms of the figure I showed before. Now the question is, if the IgM does not go under a sort of X-ray heating, so it doesn't get heated at all. So you have this brightness temperature contrast. Under the previous scenario, the spin temperature with X-ray heating just basically goes off to large values. This term saturates out to unity. But if we don't have heating at all, this spin temperature is adiabatically cool. It'll cool faster than the C and B temperature, and thus you can produce these very large amplitude signals. For example, you can get brightness temperature contrasts of order 1-200 millikelvin. And these are referred to as cold reionization scenarios because the IgM basically doesn't undergo any heating whatsoever. And so as the power spectrum is this term squared, you expect, or you can theoretically obtain power spectrum amplitudes of order 10 to the 3, 10 to the 4 Kelvin. So where would that sit on the figure I showed previously? You'd see this curve here. So this purple line here would be a representative power spectrum under these extreme models, this cold reionization model where you have no heating, extremely large power spectrum amplitude. And you can see here that these models are already in excess of the existing limits on the 21 centimeter power spectrum. So what we want to do is basically place the upper limits on the 21 centimeter power spectrum in context of reionization. Now, the upper limits are still relatively large, and so it's very easy to get models that are consistent with the upper limits. So you can't perform a proper parameter estimation and rule out models under a normal statistical inference scheme. But you can do the reverse, and the reverse is to basically, can we flip the likelihood and say, maximizing models that are exceeding the upper limits. So basically models that get further and further away from the upper limits, we call them, so we basically assign them to be the maximum likelihood. So we're looking for models that are exceeding our upper limits on the 21 centimeter power spectrum. So the reason we're doing this is because, as I said, we can't rule out models, but we can sort of start to place limits on regions of parameter space that we can sort of disfavor statistically. And all of this is performed in a Bayesian framework that I written, which is 21CMMC. And the results in the next few sections is basically applying this approach, looking for models that disfavor the 21 centimeter power spectrum, and it's just using upper limits from MWA. So this is a corner plot of 9 astrophysical models, 9 astrophysical parameters from our model. So you don't need to go into all the details of each of these parameters, but the disclaimer here is that these are the posteriors of disfavored models. So this is where you see peaks, so this is where it's most likely to have a model that exceeds the upper limit. So much more simply, what you're interested in here is up top 6 parameters are your galaxy properties. So this is the escape fraction and ionized number of stars in galaxies, and also the typical mass scales of your ionizing sources. And your bottom 3 are X-ray properties of your galaxy. So basically ones that are going to control this cold reionization scenario. Low X-ray luminosities, you're going to have these extreme cold reionization models. So in this scenario, our fraction of gas in stars and escape fraction are both proportional to the halo mass of the ionizing sources with some power law. And so from this figure alone, we can infer some sort of qualitative inferences on the astrophysics of reionization. Firstly, here, this is the normalization for the escape fraction of your galaxies. And you see a strong disfavoring of very small escape fractions. In the next one, so I'll come into that in a second. There's a slight preference for low mass galaxies. Again, this is posteriors of disfavored models. So if you're seeing a dropping away, that means that it's more likely to exist down there. So it seems like we prefer reionization driven by lower mass galaxies. Again, strong disfavoring of short time scales. And here's the main one is this X-ray luminosity. We see a strong disfavoring of very small X-ray luminosities. And this is this cold reionization scenario. We expect these values, these very low values, to be ruled out by the MWA already in these extreme cold reionization scenarios. Now, why is there a disfavoring of these small escape fractions and possibly a peak in the fraction of gas in stars? This is purely to maximize the 21 centimeter power spectrum, you need reionization to be about its midpoint, and that's where the power spectrum peaks in amplitude. And these correspond to a reionization scenario that's 50% complete at 6.5, the lowest amplitude limit from the MWA. So it explains why those values are disfavoring. It's just trying to push reionization to occur at those redshifts. One of the other things you want to look at is how this compares against existing observations. So here's a compilation of all limits and constraints on the reionization history from quasars, Lyman alpha galaxies, Planck, and Lyman alpha emitter clustering. This shaded region is envelope of all models that are inconsistent with MWA upper limits. So therefore, there are models going through these data points that would be perfectly consistent. And so this implies that the MWA is already ruling out some models that would be otherwise consistent with existing observational constraints. And the same picture can be seen in galaxy luminosity functions. Here is the observed galaxy luminosity function at redshift 6, 7, 8, and 10. And here's a compilation of 1,000 models drawn from the posterior models inconsistent with MWA. you see here, the vast majority are already would be ruled out because of these existing constraints, but there are some models that are consistent with these observational constraints. And this again implies that the MWA is beginning to rule out models that would be otherwise consistent with existing constraints. And so I shall end that there with my summary, and thank you.